Geometry Chapter 7, Lesson 4, and we want to look at similarity in right triangles. You remember that we were looking at similarity in triangles, and once we showed that triangles were similar using AA, SAS, or SSS, we then used the similarity ratio between those two triangles to determine a missing length in the other triangle. We're going to look at some special properties that happen in right triangles that are similar. Now, I want to remind you of this proportion because this is the critical part or the tie-in in this similarity of right triangle lesson that we're going to talk about, and that is these two values, which are the means, are the same. Okay, and that is the most important thing, and we need to recognize that this is called, or these are called, the geometric mean. So if something is the geometric mean, that value goes both here and here in this proportion as we move forward, and then we've determined that the geometric mean is simply then the square root of A times B. If we solve this little equation using the cross product property, you remember we determined then that the geometric mean, the value of that x, was equal to the square root of A times the B value. And that's what we're going to be looking at when we're looking at these right triangles that are similar. Now, what we're going to do is we're going to begin with this right triangle, and we're going to draw an altitude and a hypotenuse, or an altitude to the hypotenuse of a right triangle. Now, you remember an altitude goes from the vertex perpendicular to the opposite side, and then the hypotenuse, you remember, is the angle, or excuse me, the side that's opposite the right angle. Now, this is the way it's drawn in your book, and I'm going to go to another slide here where we have this right triangle both drawn two different ways. So this is the right triangle that we have. Now, when it's drawn like this in the bottom right corner here, the right angle is up here. Okay, so let me draw a little right angle mark. So that's our right angle mark. So the hypotenuse would be this leg that's on the bottom. Now, if we draw an altitude to the hypotenuse, you'll notice that this cuts that triangle into two more right triangles. And what happens is we have three right triangles then. We have the original right triangle, which is in yellow. We have this smaller right triangle, and have this medium-sized right triangle. And what happens when we draw this altitude to the hypotenuse is it creates these three right triangles, and all three of these right triangles are similar, which means they're all proportional, or the sides are proportional. And if we set these proportions up in a particular kind of way, we have three unique properties that we can use that involve the geometric mean. So I'm going to kind of explain what those properties are, show you what they are, and then we'll look at how we can use those. Now, I've taken this triangle down here that was drawn like this, and I've turned it around so now that it's up, standing up where we're more into something that we're more used to seeing, something that's drawn like this. So here's my right angle. So you can see I've kind of flipped this around. Now, what I want to do is to label the sides of this large right triangle, this original right triangle, and I'm going to label this side X, this side Y, and then I'm going to label this side Z. Okay, and that's the hypotenuse. Okay, now I want you to notice that in this right triangle, of the two legs that are not the hypotenuse, Z is the hypotenuse, of the two legs that are not, one is much longer than the other. So X is what it would be the longer of the two legs, and Y is the shorter of the two legs. So I'm going to shrink that down just a little bit, but I am going to label these the same way. So this is X, it's the longer of the two legs. This is Y, it's the shorter of the two legs. And now this is Z. Okay, now Z is that entire length. Okay, so I want to kind of move this out here. And I want us to remember that Z goes from here to here. Okay, so try to draw this. So Z goes from here to here. Okay. Now, if we take a look at this blue triangle here, and we were to put this blue triangle here, and again, I'm going to bring this one out here so it's drawn the other way. Notice that this X value that was the longer leg of the original one is now the hypotenuse of this blue one. In other words, here's our right angle because the altitude was drawn perpendicular. So now opposite that, so in the blue triangle, the x value is the hypotenuse. Okay, and then this longer of the two legs is not the entire hypotenuse of the other one, but this will be the longer. I'm going to label that A. So over here, this would be the longer of the two legs. And then this one would be C, or the shorter of the two legs, so I'm going to put that here. So I've taken that triangle and kind of flipped it around and labeled it out here. Okay? Now, let's see if I can't do this here. I don't want to move that one. Let's just do it this way. So we're going to erase that, and I'm going to write that up here. So here's my C. Now, if I take this smaller triangle, and let's put that here, and again, because the altitude is perpendicular, this is perpendicular, you'll notice that in the orange triangle, that the side opposite, this y value, which is the shorter leg of the yellow one, is actually the hypotenuse of the orange one. Okay, so this is actually y. Okay, and you'll notice that the longer of the two legs is the same as the shorter of the two legs in the blue one. So this one is the longer of the two, so this one is going to be C. And then I have this part of that longer, that hypotenuse of the original, well, let's label that B. So here we have B. So here we have our three triangles, and we know that all of these are similar to each other. So let's look at three properties that are true that from this original one. Now I'm going to label these triangles. Let's label this original triangle as triangle 1, and we'll label this bluer one as 2, and this orange one is 3, just so we can kind of keep those straight. So we have this original right triangle where we draw an altitude to the hypotenuse side of that, and then we have these different lengths within that triangle that we are going to be able to determine using the similarity of these three triangles. Now, the first thing we want to do is compare triangle 2 to triangle 3, and I'll notice that there's a C in both of these, so I'm going to compare A with C. So this is the longer side of the blue one and the longer side of the orange one, and then I take the shorter side of the blue one to the shorter side of the orange one, and you'll notice that we have the same value in the mean position. So C, then, we could say, is the geometric mean of the lengths A and B. So if I know what A and B are, I can determine the length of C. I simply calculate the geometric mean of A and B. If I know A and C, I can set up a proportion and determine the length of B or of A. Just remember that the length of C will go in both places, the geometric mean position. Okay. The second property we want to look at, or that we know, is if we compare triangle, let's say triangle 2 to triangle 1. And you'll notice that in both of these I have an x. So let's see if we can't compare the x. So the A of the blue triangle goes with the x of the original triangle, and therefore the x of the blue triangle goes with the z of the original triangle. So again, you'll notice that x is the geometric mean of A, which is this part of the hypotenuse, and z, which is the entire hypotenuse of the first triangle. So x then is the geometric mean of A and Z. So this length of this longer leg in the original triangle is equal to the geometric mean of the longer side in the blue triangle and the hypotenuse of the original triangle. So this is the second ratio that we want to make sure we understand. Now I'm going to move this last triangle down over here so I can fit this. And in our third ratio, or a third thing we want to look at, is if we were to compare triangle 3 with triangle 1. And you'll notice that both of these have a y in them, so let's compare the y's. So in the original, or in this orange triangle, y goes with the y in the yellow. So I have b, if I compare that to y, is equal to y compared to z. And again, you'll notice that y is in the mean position, so y is the geometric mean of b and z. Now, whoops, b and z. So you'll notice y, which is a leg in the original triangle, is the geometric mean of this smaller section of the hypotenuse that was cut by this altitude and the entire length of the original triangle's hypotenuse. So that's the math behind these relationships, and what we really need to do then is just have a way of memorizing or organizing this information so we can use it. And basically what it comes down to is this. When you draw an altitude that goes to the hypotenuse of a right triangle, then the length of that altitude is the geometric mean of the two pieces of the hypotenuse. And this is the proportion. This is the altitude. These are the two pieces of the hypotenuse, and we can either set up this ratio and proportion like this, or we can simply calculate it if we have the correct information. The leg of this original triangle, x, is the geometric mean, so it would go in this mean position, of this A piece of the hypotenuse that's connected to the x piece, and then the entire length of the original hypotenuse. So the leg of the triangle is related to the hypotenuse of the triangle and then the portion that's been cut by this altitude. And then the other leg of the triangle is the geometric mean of this little piece that's connected to it, along with the entire hypotenuse of the original triangle. Okay, so those are the three relationships that we need to know, and those are the relationships that are created when we draw an altitude to the hypotenuse of a right triangle.